Welcome to today's explainer, where we're going to dive into the surprisingly elegant math behind keeping dynamic systems stable. Whether you're working on a robotic arm, tuning a self-driving car, or just messing around with an automatic tracking camera, controlling these systems without them shaking, vibrating, or just completely falling apart is a massive challenge. So today, we're going to unpack a totally brilliant visual tool that engineers use to tame all that chaos. We've got a really fun roadmap for today. We'll start with the core control system problem, meet our hero, the root locus, go over the sketching rules, walk through a real mathematical example, and finish up by designing for actual stability.
All right, let's jump right into section 1, the control system problem.
To really get why this math matters so much, let's ground it in the real world. Picture an auto-tracking security camera following someone walking by. If the person moves fast, you obviously want the camera to react faster. So naturally, you reach for the dial and turn up the gain, which is just the parameter that controls how aggressively the system responds. But if you crank that gain way too high, the camera overcorrects, shoots past the subject, tries to hit back, and suddenly it's just spinning wildly out of control. So the million-dollar question is, how do you push a system to its absolute peak performance without breaking it? It's honestly exactly like turning up the volume on a microphone. You know the drill, everything sounds great, it's getting louder, until out of nowhere, bam, it hits you with that awful, piercing feedback squeal. Increasing a system parameter blindly is a one-way ticket to dangerous instability. We need a way to mathematically visualize exactly when and why that squeal is going to happen, long before we ever build the hardware. Which brings us nicely to section 2, meet the root locus. To solve this, we actually have to travel all the way back to 1948. An engineer named Walter R. Evans was pulling his hair out over complex aircraft flight control systems. To predict this terrifying instability, he invented a graphical technique that is frankly a literal engineering superpower. He found a way to solve nightmarish differential equations using absolutely nothing more than a pencil, a protractor, and some graph paper. He called it the root locus. Okay, so what actually is it? The formal definition says the root locus is the path of the roots of a closed-loop characteristic equation traced out in the complex S-plane as a system parameter varies from 0 to infinity. I know that's a mouthful, but essentially we're just drawing a treasure map. We're tracking the journey of a specific parameter, usually the gain, which we call k, to map out the exact borders between a stable system and a totally broken one. Now, the absolute genius of Evans' method is right here. We look at two things. First, open loopholes. These are static, known variables that are super easy to find from our components. Then we have closed loopholes. These are the chaotic, dynamic variables that actually dictate what the system does when it's running. Evans figured out how to use the static, easy-to-find open loopholes to perfectly draw a map of the wild, unpredictable closed-loop behavior. So, how do we draw this map? Let's get into section 3, rules for sketching. Instead of just guessing, Evans gave us a really beautifully structured visual recipe. Step 1, locate your open loopholes and zeros. Step 2, sketch the segments on the real axis. Step 3, draw linear asymptotes. Think of these as the highway lanes shooting off into infinity. And step 4, figure out the breakaway points, which is where the paths actually crash together and launch off the real axis. It turns an entire textbook of algebra into 4 completely manageable visual steps. And if you remember absolutely nothing else, remember this golden rule of the road. Every single branch on our map has a strict starting line and a finish line. The paths always start exactly at the open loop poles when our gain is at 0, and as we crank that gain dial up toward infinity, those paths travel across the graph to finish at the open loop zeros. All right, let's put this into practice. Section 4, example problem walkthrough. Let's look at a classic third-order system. Our equation here is 1 plus k over s times s plus 1 times s plus 2 equals 0. Let's say this represents that auto-tracking camera from earlier. We're going to turn up the gain, k, and just watch what happens to the mass. Following our recipe, step 1 is marking our starting lines. By checking the denominator, we easily see our open loop poles are at 0, -1, and -2. Since there's no s up in the numerator, we don't have any finite zeros. And because we have exactly 3 starting poles, we instantly know our map is going to have 3 totally distinct paths, or branches. Moving on, we need our asymptotes, those guidelines pointing off to infinity. To find the center point of those guidelines, we just take the average of our poles. 0 minus 1 minus 2 equals -3. Divide that by our 3 branches, and you get -1. It's really that simple. -1 is our exact centroid. It's the anchor for our whole drawing.
Okay, so we're anchored at -1, but which way do we point? Evans' rules give us 3 specific angles based on our 3 branches: 60 degrees, 180 degrees, and 300 degrees. So radiating straight out from that -1 center, these lines show us the exact flight paths our poles are going to follow as that gain dial stretches up higher and higher. Now here's where it gets really dynamic. As we start nudging the gain up from 0, the poles sitting at 0 and -1 start drifting toward each other, and smash! They literally crash into each other. With a tiny bit of calculus, we find they collide right at -0.4226. At that exact decimal, the roots break away from the horizontal axis and rocket vertically into the complex plane, perfectly tracking those 60 and 300 degree guidelines we just drew. And right here is the danger zone. As the gain gets higher, those vertical paths are heading straight for the imaginary axis, which is the absolute edge of the cliff for system stability. If we do the math, they cross the line exactly at positive and negative J 1.414. And guess what the gain dial reads at that exact moment? 6. When K equals 6, we are literally 1 millimeter away from complete system failure. Now that we've sketched the danger, let's talk about Section 5, Designing for Stability. With our hand-drawn map finished, we can build this beautifully simple table. We now have strict, undeniable boundaries. Keep the gain under 6, the root stays safe on the left side, and our camera tracks perfectly. Turn it to exactly 6, the system oscillates, the camera just wobbles back and forth. But if you're brave enough to turn that dial past 6, the roots cross into the right half of the plane, total instability. The camera vibrates itself to pieces. Now I can basically hear some of you, through the screen, wait, isn't doing this with a pencil super tedious? And yeah, you're not wrong. Today we don't actually need the protractor. We have controlled design software like MATLAB. You just punch in RL locus and it spits out this entire flawless map, pinpointing any gain value in literal milliseconds. Which honestly leads to a really fascinating question about how we learn engineering today. If a laptop can instantly plot millions of points and draw a perfect root locus while we sip our coffee, why on earth do we still force people to calculate centroids and breakaway points by hand? It all comes down to this. Software gives you the exact answer, sure, but the sketch? The sketch gives you the intuition. Understanding the root locus, actually seeing why paths crash, or how adding a single 0 can physically pull a failing system back from the brink, that changes how you see the world. It takes you from just being someone who types numbers into a screen to someone who feels the physical heartbeat of a dynamic system. So the next time you're looking at a wildly complex piece of tech, you've got to ask yourself, do you just know what it outputs, or do you truly understand its roots?